Okay, so in this brief video, I'll try to point out what is available in the literature regarding the CMUTs, which has been built on very thin substrates. By thin, I mean the dimension, physical dimension of the substrate is very small compared to the uh, longitudinal wavelength that is going to be propagated into the solid. So the acoustic fields and waves, the impedances that they suffer in solid is very different from that of the fluid medium. So um, I'm going to talk more about that later on. But first off, this is a very useful reference in GFFC, published in 2003 in Stanford. And what they has is a long rectangular membranes. They're not circular. Okay, so they're 1 centimeter long, 77 micrometer wide, and you see that on the top of the rectangular membrane, about half of the area is covered by aluminum electrode. And the other electrode that is not shown in this figure is what they say is the thin film of highly doped silicon. Substrate is also silicon, and when they harmonically excite this rectangular membrane of 1 micrometer thickness, what they record is for the structure, geometrical parameters of the structure, they record that the fundamental resonance occurs around 2.1 megahertz. There are other uh, uh, small peaks that is evident that are evident over here. These observations that they claim in the paper are due to the reflections off from the posts or the structures in the CMUTs. So, and these reflections are primarily in the range from 1.6 to about 1.8 megahertz. Yes, you can see this in the imaginary part as well. Yeah, but the point is, you see this baseline of the real part. It's not straight, right? It's not flat. It's not zero. It has a certain rise over here, which means that uh, which is assumed to be a leakage into the backing, silicon backing. So it falls with the frequency, and at higher frequencies, it is the resistance is much smaller. Okay, and they have tried to calculate the resistance of the leakage that they have into the silicon substrate, and that's quite different from the radiation resistance of air or fluid mediums or materials like soft polymers having Poisson ratios close to 0.5. So what they are pointing towards is that they have this Doppler vibrometer measurements, and they claim to have to observe the lower order Lamb wave mode. Uh, A naught is a transverse Lamb wave mode, whereas naught is a symmetrical longitudinal mode. So if you see again the uh, resonance of 2.1 megahertz and consider this with the relate this to the plate thickness that is 18 micrometers, so the device operating characteristics becomes about uh, 36, yeah, about 36 or 38 um, hertz into meter. Okay, and if you convert this into kilohertz per meter, then this is 0.038. That's the device operating point, and at that device operating point, you don't have the higher order modes. You are somewhere around very close to DC. So okay, so you have a certain amount of energy that is being coupled to the substrate in form of A naught modes because of the harmonically excited membrane that creates maybe non-uniform tensile stresses uh, into the backing, into the silicon backing, and because of the power of these lower order modes that are propagating down in the silicon substrate, and because of that, you see small leakage or the baseline in the real part, and also the measured Q is not is lower, so because of this loss. Okay, so they tend to include this radiation resistance loss into the silicon substrate. Okay, besides what the membrane experiences in the top medium. So there are two radiation mediums. One is the top uh, and air. One is the air, and the other is the silicon, which is which is on the other side. So the membrane is connected through post, and that's where it couples energy uh, into the substrate. Okay, so at this particular operating point of 0.038 kilohertz, in figure B, you see the zoomed in version of A naught mode, and the velocity of sound is about 740 meters per second for A naught mode. For S naught modes, well, yes, S naught mode retains a higher um, and stable velocities for vanishingly thin plate thicknesses, as is suggestive of these dispersive relations of Lamb waves. But if the thickness of the plate increases, well, then we have to include the higher order mode as well, as being suggested of this dispersive relations. So if the, for example, if the thickness of the plate increases, then both the A naught and S naught mode, they achieve a stable Rayleigh velocities. Yeah, but over here, for very thin substrates, um, you don't have higher order modes. You have all the energy that is being coupled is in the form of A naught, and some of the modes are S naught. So only two lower order modes of Lamb waves are involved in coupling of energy into the substrate. Okay, they're in the form of A naught and S naught. So you can see uh, they have the electrical circuit over here, and they have included R substrate, and to be consistent with the convention of circuits, what they have done is to evaluate first the power of the normal modes and divide that with the absolute square of the particle velocity of on the membrane. And because you see the current in the mechanical section is the particle velocity over the membrane, and it's the velocity that corresponds to the to the to the power that is being coupled into the ultrasound medium. And in this case, this medium is you can see this meshed medium in a 2D axisymmetric model in FEM is silicon, and a certain part of that um, is attached to a lossy silicon. Well, why do they have lossy silicon? Is what they say is that you don't need to you don't need standing waves in silicon substrate, so the loss factor is selected such that it's like an absorbing boundary which does not create any reflection, so you don't have just like a perfect matching layer. You don't have reflection. You don't have standing waves. Okay, so it damps so it absorbs all the waves coming out of the silicon. Okay, so this harmonically vibrating silicon nitride membrane creates tensile stresses, and what they use is a normal mode theory of plates that all the normal modes can be linearly combined or superimposed to form the velocity fields and the tensile stresses. And this can be solved from the equation of motions. An is the amplitude of the normal modes. The subscript n is denoting the normal mode of the velocity, and this is the uh, tensile stress. So the average normal mode per unit length is given in terms of the velocities, normal mode velocity, and the tensile stresses. And from that, that's how they calculate the power per unit length. And if you have an, then you have the power, and this power goes into this relationship. And if, with the velocity, you can find the sink or the energy loss associated with our substrate, which the substrate is posing or giving to a harmonically excited silicon nitride membrane. Okay, so that's the resistance that silicon nitride membrane is experiencing while it couples normal modes of Lamb waves into the silicon substrate. Okay, and this plot is um, quite different from what we have in air. For example, in air, you have like a rising trend, or fluids. It rises with frequency before it reaches a plateau region at very high frequencies. But for solids, you see it has a sort of like a dropping characteristic. It looks like that with increasing frequency, because these devices are built on 18 micrometer substrate, and they're exploiting this loss to make CMUT based Lamb wave devices, because the vibrating membrane is generating Lamb waves into the substrate. So the resistance, in accordance with the circuit convention, is the other way around. It's like decreasing with increasing frequency. Okay, And because the first lamp wave device, what they report is that was built on a 500 micrometer substrate, and the radiation resistance that they calculate for it is a very similar shape to what 18 micrometer is. So there is an uh, order of 2 magnitude difference. Uh, 18 micrometer substrate is supposed to uh, have more resistance as compared to 500 micrometers. Yeah, so I think they're missing this negative sign. So this has to be 10 to the -3 and -5. If so, uh, if the claim is that this is a dropping characteristic with frequency, the radiation resistance is a negative slope. Okay, then it has to be negative scale. I think these are missing over here. Stanford -2, -3, and -4. Okay. Um, so the resistance, the radiation resistance, is different from what we have in air or fluids. So that is something to get ourselves familiarized with if you practice in acoustics. Um, this well, this calculations are again from ANSYS finite element analysis package, and shows that the force on the top electrode is larger than the force on the bottom electrode, and most of the energy that the membrane couples is around the resonance. That's about 2.1 megahertz. So these are three configurations. One is with the dotted line is for the force calculation on the top electrode. You have force on the bottom electrode, which is dashed dotted line, and then the third force calculations are on the both of the electrodes. Okay, so yeah, now they compared this with the uh, so in their paper they said that they have this experimental solder line. This is for a 350 micrometer substrate with 15 rectangular membranes. And so why they have 15 rectangular membranes? Well, they say that they are one wavelength apart to foster constructive interference, and they are using that as for sensing of lamp waves. And they're again 15 rectangular CMUTs. Those are sensing the lamp waves generated by an 18 micrometer uh, CMUT device. But the difference over here is that if the device is built on 18 micrometer substrate, which generates lamp wave modes into the substrate, you can compare the bandwidth of for the same geometrical dimensions. So you can compare the bandwidth on 18 micrometer substrate and 500 and 350 micrometer substrate. It appears that it appears that at 18 micrometer substrate thickness, the bandwidth of resonance is more. So it's a lower Q as compared to what you have for 350 micrometers, and that is evident from here. The thin substrates, they uh, give more resistance to the vibrating membranes. So you have like a larger bandwidth for or a lower measured device Q quality factor for thin substrates as compared to thick substrates. Okay, this is also thin compared to the wavelength. If you consider the longitudinal velocity of sound in silicon as 8,400, then that means that the longitudinal wavelength is about 4 mm, and in the silicon substrate, and this thickness is negligible. Even 500 micrometers is negligible for it's a very small fraction of 4 mm, right? So again, it's a case of thin substrate. It's not a solid backing. It's not a rigid backing. It's a thin backing compared to the wavelength, longitudinal wavelength of ultrasound in the silicon medium. Okay, yeah. So the main point that I want to emphasize is that the radiation resistance that they calculate from calculating the power of the normal modes into the silicon substrate and the velocities of the particle velocity of the membrane that couples those modes, the radiation resistance that they find out is very different from that of air, which is referenced over here. It has a negative slope and it drops with increasing frequency. So it looks like that more leakage um, occurs at DC or low frequencies, and at higher frequencies this loss is less. Okay, and that is something that is responsible for creating this sort of a baseline over here. This A naught mode is coupling because of that A naught mode that is going into the substrate. You have this sort of a baseline that can explain this elevated impedance, real part of the impedance. Okay. Well, this is another case that I've talked before in my videos. So these are the CMUTs built in Bilkent University in about in 2018. So they also have this. These are wafer bonded streamers, by the way. So they have a silicon membrane and then they're bonded to the glass substrate. But the glass substrate in this case is again 500 micrometers thick, 0.5 mm. It's very small compared to again to the wavelength of the sound in the backing. Yeah. So you can see the resonance frequency is like 77 kilohertz, and if you calculate for the longitudinal speeds of glass, which is 5,600 meters per second, then that wavelength is about 70 mm. And 70 mm, if you compare 70 mm with 0.5 mm, also very thin backing. So we can have a very thin backing case for this wafer bonded CMUT. And you can see the point is the same, that radiation resistance uh, is sort of having a negative slope. It decreases with frequency. It has more leakage, or it could be, if not Lamb waves, it could be elastic waves. Both shear and longitudinal modes are supported in solids, and glass they can be supported. So you have more leakage, more resistance at low frequencies compared to what you have at higher frequencies. So there's less leakage, but this affects the device Q. So that can be reproduced in the circuit model if you include the shunt uh, substrate loss, which is very high in case of a rigid or solid backings. If you do not, like, if you open circuit that, then you have very high Q. You don't have this baseline. You don't have these baseline trends. And but this Z substrate is responsible for sort of creating this dropping characteristic with frequency. So this is a loss. This is a mechanical loss which models the damping of elastic waves in solids. Okay. Yeah. So if you look at the substrate impedance for this particular CMUT, you have the same trend. Okay, which Stanford people have reported like this. So it sort of, the radiation resistance decreases with frequency. Okay. And over here as well, it is decreasing with frequency, and it has the capacitive part as well, which might model the compliance, because the the glass backing or the substrate is like a stiffened spring. It's a hard spring to move, as compared to the silicon that you have on the front side. It has its own compliance and mass, so you have a like a much smaller capacitance and less compliant capacitance in the backing. Okay, so that's what it is, and this is a loss capacitance, which together with the compliance of silicon uh, transformed to turns ratios goes into the electrical side with C0, that is electrical capacitance CMUT, with parasitic capacitance to produce the effective capacitance of the CMUT cell. Okay, yeah. So yeah, this is another. This is CMUT2. This is another CMUT on the same wafers, same glass and silicon wafers built on the same wafers, but the trend is the same. You have more leakage at low frequencies as compared to higher frequencies, and this is what creates those baselines. And this loss is frequency dependent. It's an impedance, and it turns out that to fit this or to explain those losses, you have to include substrate loss, which accounts for the damping of those elastic waves in the glass medium, and the radiation resistance that you are using has a negative slope. It's not negative. The slope is negative. That is, it drops with the frequency. Okay. This is yet another relevant reference, and these are again built in again presented and built in Stanford, and they were presented in IUS meetings in 2004, and they also have this sort of they also claim to have more leakage at DC compared to higher frequencies, and they were building very high frequency CMUT linear arrays with thin backings, and the intent was to use them for high resolution imaging uh, for for medical diagnostics. So, but the impedance that they show is having for these wafer bonded CMUTs that they build, they were very similar phenomena that they observed with the measured real part of the impedance. It rises with frequency. It drops with frequency. It has a more rise at low frequencies, and then it drops. Okay, so this is a very relevant reference in the literature that exists. So what they did was the interesting thing that they do was they had to package these arrays into an intravascular probe for imaging. So they built ring arrays, again high frequency ring arrays for more spatial resolution. But to aid into packaging, they had to thin down the substrate to about 200 micrometers, and 200 micrometers is nothing compared to this operating device characteristics, the wavelength in the back silicon. So if when they thinned it down to 200 micrometers, they have a sort of they still have this baseline, but the effect is much reduced. You can say that okay, the baseline is gone, but still um, what they have over here is very high ringing in the measurements. So they're still coupling energy at the low frequencies. So at low frequency, you still have more noise, substrate noise, as compared to what you have at the high frequencies. It's less. Okay, so these are just the references that I found very useful in just checking out what exists in the literature for wafer bonded CMUTs. You can see uh, these are the ring arrays built on a. This is the picture is about 2.5 mm, and dimensions are such like that. So you can see that they're very small devices, and they have the backing is about 200 micrometers. Okay, it's a very thin backing, but still for these thin substrate, you still have uh, substrate noise, which creates those baselines, and it overall contributes to the overall noise and lowers the quality factor of the CMUTs. Okay, yeah, so that's all. I'll just put these references into the video description, and if you want to learn more, please refer to these this published work. So thank you for listening, and have a good day.